heard an illuminary lecture from Professor Sutkov regarding a blending of basic science and medical science, and very much attractive. So from there, I'm taking you to another field in material science, which fascinates me particularly because of the kind of materials which are multifunctional. Now, what is multifunctional means that, see, these are the days where you need a single device to do many functions. In your mobile phone nowadays, you do have WhatsApp, you can write stories, not only in telephone, but you do so many Google searching, so many information. That means a single device or even a single material which can have many functions. And so in search of such materials, we got a few materials. So I just want to tell. See, these days there are materials with magnetic and metallic properties or even superconducting properties. Nobody was initially thinking that plastics can be conducting, but in 1970 it came. But in addition to those, you need the miniaturization. See, earlier used to use the electronics laboratory, means a huge vacuum tubes involving computers having a big size of rooms, but they are in present days, they are in the almost palm size computers you can have. So miniaturization, and there the concept of the nanoscience and nanotechnology brought a big revolution. And in these materials, you can have the structured form. That means the directional things, nanorod, nanotube. Then they can bring the novel because of their directional property. So I am just confining my talks in three aspects. One is a class of this material called perovskites. I've got particular fascination for those. They can be acting as multifunctional materials. Besides those, I will just deal upon some of the multifunctional nanostructures developed at the center from which I retired, that is Variable Energy Cyclotron Centre, and other nanostructured materials. Now, this perovskite, you see, it's a typical compound with a face-centered and body-centered thing with ion in the. Oh, sorry. Oh, not that thing. Achha, this. It's a non-transitional element, and the central one, the transitional element. This transition element, I think, because of all chemists I can share with you, that they have very peculiar properties. They can have the valence changes, and thereby they can be employed as the redox agents, which is very much useful as they're used as a pseudo-capacitive material. So they can have large value of capacitance because of these Faraday's redox reactions. Now, we can have one-dimensional quantum dots like nanoparticles, nanowatts, these are having one dimension, or nanowell two-dimensional. In addition, people are interested in making the composites of these nanomaterials, just like the even polymers of the E dot and nickel ferrite. This acted as a very good nanocomposite as supercapacitive materials. Other nanostructures like graphene is nowadays very popular material. This is also having a very large value of this pseudocapacitance because of its pi electron network, which can be useful for the kind of electron transfer. You see, any redox reaction is dependent upon the electron transfer. And graphene is a fantastic thing because of its extended conjugation. And I think a new generation will come when we'll be having one-dimensional carbon wire also with sp hybrid network with so many pi bonds. Anyway, role of the nanostructure. We first did some nanocomposite systems with polymer of E dot and nickel ferrite. Because of the nickel ferrite being incorporated as a nanocomposite, there was an increase in the capacity, specific capacitance value to 251 farads per gram. Then we did some work on graphene-based supercapacitor. When graphene was modified with nitric acid, then its capacitance increases to 180 farad per gram. Also, we had worked on some sonochemically synthesized. In sonochemical techniques is a bit new technique nowadays employed, where instantly, because of the rarefaction and compression cycle, a huge power density is generated and huge temperature, which can be employed in synthesizing the nanoparticles by breaking the molecules. So delta MnO2 and graphene nanocomposite superconductor, they were capacitance value of 355 farads per gram. Now we come to the perovskites. Now bismuth ferrite nanowire, this we developed by simple chemical means using the porous anodized alumina template with pore size of 20 nanometers and above. Now here the growth is controlled by the pores of the template. The simple controlled vacuum filtration technique was employed using the sol-gel technique of bismuth nitrate and ferric nitrate. This is the schematics. The methoxymethanol was a solvent, and bismuth nitrate and iron nitrate was employed in anodized alumina templates by vacuum filtration. Then we sintered at 700 degrees centigrade, and we ultimately got these nanorods. See, this is the FESEM site, and cross-sectional FESEM gives you some kind of values of, you see the protruded things within the pores. These are the nanorods of bismuth ferrite. This will be very clear in this thing. Around 1 micron length deep in this nanopore. So 1/60th the light is exposed outside. And this is the portion of interest to us. This is the usual transmission electron microscopy, and selected radii electron diffraction shows that it's of polycrystalline nature. This is the X-ray diffractometer. These are not the material. This is anodized alumina. But you see a small characteristic peak of 110 of this bismuth ferrite, which shows the presence of this in the material. This is the typical cyclic voltarogram. Of course, it is not very good because of the fact that it is admixed with the alumina, whose CCV is like this. So now the total charge here is both the charge outside and the portion which is introduced in the pores. So to extrapolate the charge in the outside, if we plot the Q versus V to the power minus half to 0, then we can get the intercept as Q out. And for bismuth ferrite nanorod, which is protruding out, that Q out is relevant. And we got a specific capacitance to be around 450 farads per gram. And this is the galvanostatic charging, discharging. This was fairly repeatable, and charging and discharging time was fairly similar in values. So in summary, these multifunctional materials in nanostructured forms are of immense interest, and we had carried out studies on different types of nanocomposites and with respect to specific capacitance and development of bismuth ferrite in form of nanorods and nanowires. And bismuth ferrite nanorods displayed large value of specific capacitance, which may be important as the pseudo-capacitive materials. So my collaborators, mostly from Variable Energy Cyclotron Centre, and She is one postdoctoral fellow. Subhasis Rana was postdoctoral fellow. And these are the facilities available at our center. So if anybody interested, she can have contact with the people. Okay, thank you.